In this video demonstration, we're going to give an introduction to one of the many tools of machine learning, something called the artificial neural network, which is abbreviated ANN. So what exactly is an artificial neural network? It's a mathematical structure that can help you come up with an empirical model to represent relationships between inputs and outputs in the real world. So this mathematical model can be used to represent some pretty complex relationships between inputs and outputs. Is it a black box model? In some senses, you could consider it to be a black box model because the math isn't totally physically meaningful to you, but it's not black box in the sense that you really have no idea what's going on in a mathematical model, just like a polynomial fit or some other empirical model. You know exactly what the math is, what the parameters are, and what the equations are, but it just may not be all that useful for a physical interpretation. One of the nice things about artificial neural networks is that they can basically give you an unlimited number of model parameters. So given a set amount of inputs, you can add as many equations and as many fitting parameters as you want so that you can represent, depending on the complexity of the process you're trying to model, you can adequately represent it. Model size or number of parameters should never be an issue, although there may be different issues. So a neural network is called this because it's designed to mimic the brain. So it's composed of neurons. So these guys in the middle are known as, I guess everywhere actually they're known as neurons, but these in this hidden layer have a response where they activate given a certain inputs or certain external stimuli. So just as the brain stores knowledge by firing chemical and electrical signals from one neuron to another, and as we learn and gain life experience, that information is all stored in just a huge number of neurons that happen in our brain. That's what an artificial neural network is attempting to do. It is not a model of the brain itself. In fact, the brain is way more complex than any neural network that has ever been created by anyone, but it tries to catch that same basic principle just mathematically. So what are some applications of neural networks? So really there are a whole lot of applications, and here are some examples, just some that I've brainstormed. So there are classification problems where you're trying to use a neural network to decide, does something belong in a particular group? So one example of this might be image recognition. So facial recognition software could use something like a neural network where it's taking in data, so pixels that tell something about the color and location. You could take all that data, and if it's a high resolution picture, there would certainly be a whole lot of data inputs into a neural network, but then you could use that to identify, does this set of data match a particular face? So that's could be an application of neural networks. Another one could be for military applications, similar image processing application where you could set up cameras and sensors somewhere and train those cameras and sensors to identify military tanks, for example. So you could feed in a lot of data from video cameras live, have a neural network process that, and then basically have the output of that neural network be, is there a tank in this picture or not? So there could be military applications, really all kinds of applications. So you could use these for speech recognition. You can use these for abnormal event detection. So basically giving a neural network a bunch of data from a process and using that neural network, training that neural network to determine if something has gone wrong in that process and if a human needs to go take a look at if there's something to fix. And I'll talk more about what training actually implies. These models are sometimes called learning models. So they're really just empirical regression-based models, but some of the buzzwords are that they learn, that you train them, and I'll get into more of a mathematical description of what that means. So another example of a neural network could be customer purchasing patterns. Places like Amazon, for example, could track your purchases and put you into some category based on all the data you've given them, what things you're browsing on the internet, what things you might be inclined to buy. There have been studies where certain online retailers can determine if women are pregnant or not based on things they've viewed. So they know they can use that data to basically send targeted advertising to them for pregnancy products or for childcare products. Just an example. There really are a lot of different applications, and really they are endless. So you could also use these for regression. Rather than just lumping things into groups, you can use a neural network to do something like forecasting, and I'll give an example of a forecasting application later in this presentation. You can use a neural network-based model to predict a process and what are the optimal points in a process. So you could couple a neural network-based regression model with an optimizer so that you're using that model to find the optimal points via the optimizer. This could also be used to actually control a plant if you have a complex relationship between outputs and inputs and you're trying to regulate a certain output. That neural network can provide a lot of insight into what the inputs should be so that you get the output that you desire in a control application. You could use this to make predictions of the stock market, provided that you give this neural network enough data and have enough confidence. You could certainly model performance of certain stocks based on certain inputs. And again, these are really complicated problems, and there's really a lot of work that needs to go into it on the manpower side, but you could attempt to do some of these things with neural networks and certainly have success in a lot of these different areas. So again, there are many more applications for regression, and I'm putting in the caveat here. While I've kind of brainstormed some potential things that neural networks can do, and I've actually applied many of these in my research and found that they work great for forecasting applications or for real-time optimization or for model predictive control, it doesn't necessarily mean that neural networks are the best tool for solving these types of problems. There are certainly a lot of different tools. Some of them could be classified as machine learning tools. So neural networks are one subset of the machine learning toolbox, but they can be powerful, but it really does take some engineering, and it takes a pretty good understanding of what's going on in the model and in fitting the model. And I'll try and highlight some of those issues as we go through. One thing to be careful about is that you could classify this as an artificial intelligence application, so you need to be careful that when you deal with neural networks that your code doesn't become self-aware and try to take over the world. Totally kidding. That's never happened to me before, but just a joke. Nerdy YouTube video engineering joke. So what does a neural network look like? I showed this picture before. You have inputs. This is something called a three-layer perceptron, which is a subset of what's called a multi-layer perceptron. And basically, you feed in inputs. So whatever, as an engineer, whatever you can determine, whichever inputs you can determine are important, leading to a certain output, you can give your neural network enough data on those inputs so that eventually you get some output. So this first layer is called the input layer. This middle layer is known as the hidden layer. So this hidden layer contains these activation functions, and I'll explain more about what the activation functions do and what they look like. But basically, a lot of the real data that's stored, that's learned by this model, is stored in the parameters that are associated with these activation functions. And then finally, you have an output layer. So it's just a mathematical structure where you take in inputs, you pass those inputs through certain functions with different weights as the adjustable parameters, and then you pass those through these nonlinear, typically activation functions. Then you have another opportunity to apply weights, which are also known as fitting parameters. And then you have this output layer, which is just basically just combining all the data from these different inputs. So this is also known as, this particular structure is also known as a feed-forward neural network or a static neural network. And it just basically means that you're predicting steady-state data. You're changing inputs and you're trying to see what those outputs would be at steady state. You can certainly have a lot of different structures. So you could have mechanisms where you take this signal and loop it back to some other neuron. You could have a lot of different structures. You can have multiple hidden layers. So this is a three-layer perceptron, but you could add in more of these hidden layers in series here and that would give you a 4-layer perceptron or a 5-layer perceptron. The models at that point get very complicated. They require a lot of computational power to fit. This is a pretty active area of research known as deep learning, and I'm just sort of alluding to this. But deep learning would imply that you have multiple layers and you have some pretty complex structures in the neural network. My experience has shown that for engineering applications, if you're trying to capture the behavior of a process, a 3-layer perceptron generally does a pretty good job, and you can expand the number of nodes you're using here, which gives you more model parameters and more complexity. And I've never had an application where it required deep learning, but typically if you're dealing with a lot of inputs, hundreds or thousands of inputs, you might want to explore other model structures, and maybe not something so simple as a 3-layer perceptron. So there is a lot of flexibility in the structure, so you can have different types of activation functions. You can have hybrid models where maybe you have a really good engineering understanding of a process, except for a certain part of that process. Maybe you want to model a changing heat transfer coefficient in your plant that's a function of several inputs. So you might stick a neural network to model just a particular part of a process, and then the rest of the process is done with an engineering or first principles model. Or you may have multiple neural networks that predict different parts of a process. You can certainly be clever and try to use your engineering judgment to model a lot of the process, and then use a neural network only in the parts of the process that are too complex to really dig into literature and find a physical relationship between one input and an output in a particular part of a process. So what do these activation functions look like? So remember, these are the activation functions. So they take in some linear combination of inputs. So you'll notice that each input gets multiplied by a certain weight or a certain fitting parameter. And then this neuron, this activation function, takes in these linear combinations of each of these inputs, and then it's going to apply a nonlinear function to it typically, and then it's going to spit something out, and then you can do linear combinations of that nonlinear term to give you this output function. So this activation function contains the nonlinear part. So there are different varieties, and these are a few of them. So you can have sigmoidal functions. You can have a linear activation function, but typically you'll want to have it be saturated on each end, which in turn makes it nonlinear. You can have radial basis functions. The most commonly used, I would say, is sigmoidal, which looks like this. So basically, this is one of your activation functions that's going to take in some input. So whatever you're putting in is going to be your x variable, and it's called an activation function because you can see that at some point this function activates and it goes from this constant value to a new constant value. So it activates based on the inputs that particular activation function is receiving. So the model parameters, those W's that you saw, and there are other parameters in here, can do things like for each activation function they can stretch this out horizontally, they can stretch it out vertically, they can shift the whole function up, or they can shift the whole function one way or the other. So those parameters can really change the shape of all this, and we'll talk more about how you find those parameters later. So when you have a bunch of activation functions, if you have a bunch of neurons in your hidden layer, now you're looking at combinations of these. So you could just imagine taking a bunch of these activation functions that are all responding to the input data in different ways, and you could combine a lot of these so that you're representing pretty complex behavior using linear and nonlinear combinations of a whole bunch of functions that basically look like this. So this is a hyperbolic tangent function, and this basic shape is called sigmoidal. So if it's a constant value at the low end of your inputs and then a constant value at the high end, and it has this nonlinear behavior in between. So the nice thing about this is that you can have a bunch of different neurons, and just like in a brain, certain parts of the brain store different information. So just like that, a neural network model has these different neurons, these different activation functions that can learn different parts of a process. So, for example, in a certain operating range, this particular activation function may have an output that's just constant. It's not really doing anything. But then in a different operating region, so under a different combination of inputs, this activations function output may be right here, or it may get up to this point where it turns constant again. So by taking the summation of a lot of these different neurons in response to many different combinations of input data, you can capture pretty complex behavior, but it does take some know-how and some engineering judgment and probably a whole lot of trial and error to get these things to work just right. So here's the basic math in a neural network. And this is this particular one with these hyperbolic tangent activation functions. So you have your output function is a linear combination of your different, these weights. This capital W is the weight that is applied just before the output layer. So it's linear combinations of these nonlinear functions, and you can have bias terms here. So in this case, you're summing up the outputs of all of these different neurons. So P is the number of hidden nodes that you have. M is the number of inputs. So we talked about this being our activation function. So the activation function looks something like this. So it's a hyperbolic tangent. You sum up weight times input, so you get these linear combinations of inputs, and you can have bias terms there. So the more inputs you have, you automatically get more fitting parameters. And then the more nodes you have, you get even more fitting parameters here. So the U's represent each inputs, and then when you combine these two functions, you end up with an overall function that looks something like this. So this is the mathematical structure. So I mentioned that these aren't truly black box models because you could certainly fit a neural network and then you can go and back out what all of your different model parameters are. So these ones that I'm circling now are some of the different parameters that you have in the model. So you could certainly go and back out what all of these are, and you could reproduce this mathematically without too much trouble. The problem you may run into is that you just have a whole lot of equations in there and a whole lot of parameters. So you don't necessarily need to understand all this math. And the math itself typically won't be particularly meaningful unless you have a certain reason to need to know that math. One of those reasons might be if you're trying to optimize based on a neural network and you want to take gradients of your neural network, it might make the solver solve more efficiently if you can go and plug in what the actual mathematical equations are. But there are ways around that too, where instead you could have your optimization solver ping your neural network model to build numerical gradients. So in that case, you don't really need to know the math in here. So basically the takeaway from this slide is there is math in there. There are a whole lot of fitting parameters, but because the whole idea behind a neural network is that it's supposed to learn the data for you, it's machine learning, you can basically feel pretty comfortable that if you get the general idea that this is an empirical model, it needs a lot of data to train it so that it can learn and retain all that information, you pretty much have the idea. And having a deep, detailed understanding of the math isn't quite as important because this is machine learning, so the computer is learning this behavior so that it can help humans or help a process in some way. So I'm going to go through an artificial neural network application to give you a flavor of what it might be used for a little more specifically. So if we have a problem, we want to predict how much energy a university campus will use for 24 plus hours in advance, and the only input knowledge we really have are what's the weather, what's the time, and the date. So a university campus might consist of hundreds of buildings and tens of thousands of people, and all those buildings are pretty complex structures, and those people's habits are quite complex. So there really is it's a very complex relationship where you might have 50,000 different people, all with different habits, different energy usage patterns. You have very complex buildings with different control schemes. They're trying to regulate temperatures by heating and cooling in the buildings. So it's an extremely complex process, and to go in and rigorously model that is sort of an intractable problem or a problem that's going to take thousands, if not hundreds or tens of thousands of man hours to really produce. And even after going through all of that, using specialized software to model each building and groups of people's energy consumption habits, you still might result in a model that doesn't work all that well, but it's just too complex. So a neural network can actually learn those very complex relationships for you. So if we had data like weather, so weather data, so here we have temperature and humidity, and we wanted to use that to produce energy consumption, a neural network model might help us map these inputs to these outputs. And you can see just by looking at this, there's no, I mean, there are obviously some relationships you can see that as temperature fluctuates, the energy you need for cooling kind of fluctuates conversely. So you can see, not conversely, it fluctuates in proportion. So you can see higher temperatures result in higher cooling energy consumption. So just as an example, so you can see as an engineer and as someone who's doing some analysis, there is a relationship here, but to actually predict this where you're getting a numerical answer that pretty accurately predicts what the absolute numerical value of the energy consumption is a significantly complex problem. This particular problem was solved using something called a recurrent neural network. And basically that's just the same as a feed-forward neural network. So you're taking in your weather forecast, you're trying to predict if k is your time step, so let's say you're trying to do this every hour. If k is your time step, you're using the weather forecast for 1 hour from then, and the time of day for 1 hour. You're trying to use this neural network model to predict what your energy usage or what your load is going to be 1 hour in advance. So what this recurrent network does is it says, well, we know how much energy we're using now because we have different instruments that are actually measuring this. So we could use the energy we're using now to better inform our model for what we're going to be using an hour from now. So it's just a simple time shift in your input data when you train this model. You can get a pretty good predictor. So you take the future prediction on the load and you loop that back so that you could predict now into the future. So you make a prediction for k plus 1, you take that prediction, loop it back, now you can predict k plus 2. So that's all that a recurrent neural network does. So this is slightly more complex than the feed-forward neural network, but not really much. So it's just taking past predictions and using them to make future predictions. So this particular model is called a NARX model, N-A-R-X. That stands for nonlinear autoregressive with exogenous inputs. It's kind of a mouthful, but really it just means a recurrent neural network where you take your predictions and loop them back so that you can have your model that's informed based on what it has predicted in the past. So the nice thing about this is if your prediction is off, let's say you take in weather, time, and load, and you come up with a forecast that's way off, well then you can take your actual measured load once you get to that next time step and use that to correct your model. So it has this self-correcting feature. So when it's wrong, it becomes aware that it's wrong and it'll try to make a better prediction next time. So this, as you can imagine, this type of neural network is going to be dependent on the accuracy of your weather forecast. So whatever inaccuracies you might have there will compound into inaccuracies in your forecasting model. So the further you go out, you're going to have your accuracy declining. So after fitting this model, these are basically how the results look. So we're trying to predict electric load, cooling load, and heating load using weather forecasts, using information about what month of the year is it, what day of the week is it, and what hour of the day is it. And you can see this neural network does a pretty excellent job of representing this data, where the actual measured data is shown with a solid line, then the neural network's forecast is shown with the dashed line. As you can see, in each of these applications, it's doing a really good job of predicting that data. There may be other days where it doesn't do quite as good of a job, but in general, this neural network is able to learn this behavior quite well. The uncertainty bounds are 95% confidence uncertainty bounds, and they're shown with the gray. Um, so think of those as error bars. So you can see that your uncertainty gets bigger and bigger the further out you're trying to forecast. So the summary here is that this artificial neural network model captures a very complex relationship very well. There are hundreds of buildings, there are 50,000 people using energy. There's a pretty complicated relationship between weather and occupancy and how that impacts energy usage. One of the applications for something like this could be, well, the actual application that this was developed for was so that if you wanted to optimize how the system is consuming energy over 24 hours, you want to know how much energy the system is expected to produce. So in this case, we solved what's called a dynamic real-time optimization problem that was basically trying to decide when do you store energy. So here you might want to store energy when your demand is lower so that you can extract that energy later when your demand is higher. So there are some really good applications of these forecasting models out in the real world, and this one was developed for a really practical purpose, and that was trying to save energy and trying to save money by proactively managing your energy based on this forecast. So some notes on how these models are fit. So one thing to keep in mind is that these models may not extrapolate very well. So just like the human brain, you only learn things from your own experiences. If there's something that you've never experienced before, you're not going to have any knowledge of it. So just like studying in class, you're only going to retain information that you've seen before and maybe repeated many times. So a neural network model is perfectly analogous to the human brain in that sense, in that it will only learn from data that it's given. So if you give it inputs that are outside of the region of data that you trained your model on, it might have no idea what to do with that data. So it's really important to have a lot of data. So you want to have many combinations of inputs. And generally speaking, you want to have more training data so that your neural network model has a better opportunity to learn the patterns that are contained in that data. So it also may not interpolate very well, and this may be user error in most cases, but there is a problem of overfitting the model. So you might try to use too many neurons, too many model parameters, so that it's trying so hard to fit your training data, and it may fit your training data perfectly, but then once you give it data that's in the range of your training data but not specifically contained in the training data itself, it might not know what to do with that, and you may see divergent results. So it's very important to validate what you're doing, to train the model and then give it data that's separate from your training data set so that you make sure your model can interpolate well. So a good rule of thumb, so you want to save some of your data for training and for testing. It's a pretty easy problem to get a neural network to match training data, and in fact, you could just make a really huge neural network with a lot of activation functions so that your model parameters, the number of model parameters approaches the number of inputs, and then you could match your training data perfectly, but you're going to have a mathematical structure that has a whole lot of fluctuation and a whole lot of noise, so that when it encounters data that's not contained in that training data set, it's going to be way off. So a good rule of thumb is to save 75% of your data as training data and keep 25% as testing data. So the testing data is not used in the model fitting. Instead, you fit your model based on the training data, then you run your testing data through the model to make sure that it's still valid for data that's outside of that testing data set. So the MATLAB toolbox that we'll cover in our next lecture is going to have a third subset of data, which they call validation data. So MATLAB has a little more complex algorithm to do this fitting, where it looks at your training data, it has testing data, but then it's also checking your validation data to determine when the model is ready to go, when it's done enough quote-unquote learning that it's meeting certain specifications and the model is complete, basically. So it's important to verify the neural network model on a separate data set outside of the training data, so you know how well it interpolates. And you may find in many cases that you have to go back and make some adjustments in your model. So although this process may sound extremely complex, and it is, there are some pretty nice software packages out there, including in MATLAB and in software packages like Python, that have built-in toolboxes that can make all of this really easy. And that's the whole point of this is machine learning, so it's the computer that's supposed to learn this stuff. Someone else has gone through all the trouble of coding, and there's certainly a need for developers to go in and develop this kind of stuff. But as engineers, we can just tap into these existing toolboxes, and it makes our life a lot easier. However, it is important to know what's going on behind the scenes and not to just do this blindly, because when you encounter problems, you may have no idea how to troubleshoot those problems if you don't understand the mathematical structure and the fitting routine that go behind it. So how does the fitting work? So the algorithm is actually, in some cases, and most cases I would say, it's solving a nonlinear programming problem, so an NLP problem, that minimizes the sum of the squared error or the mean squared error, comparing the model prediction from your neural network to the actual data. So this is how the learning takes place, is it's basically a parameter estimation problem where you're adjusting the model parameters, those weights and those biases that we showed on a previous slide, until you get the minimum sum squared error or the minimum mean squared error or some other metric. Those things can be configurable. So there are a lot of different algorithms to choose from, but basically you're solving an NLP problem. So the model parameters, as I mentioned before, are the weights and the biases. So these are the decision variables, or these are the degrees of freedom in the optimization problem. And this is why adding more neurons is giving you more model parameters, therefore you have more degrees of freedom. So you typically get better fits, at least to your training data, by adding more and more neurons. But remember, that's a dangerous thing because you can overfit, and then you'll find that your model doesn't actually work as well as it should when you apply it to a new data set. So usually the easiest thing to do for some of these toolboxes is assign random parameters. So the MATLAB toolbox that we'll introduce you to in our next lecture does just this. It guesses at all your initial weights. There isn't really a physical meaning to these weights, so it doesn't really matter. There's no constraints on them. You just guess a bunch of different weights. So this randomness can actually lead to some interesting issues as you go along. So you're taking a random initial guess, then you're solving an NLP problem to trying to get to the minimum sum squared error. So those parameters are adjusted until the sum squared error is minimized. So the other issue here is that as a nonlinear programming problem, these are highly non-convex, which means you're going to get many, many local minima, maybe hundreds or thousands of local minima in your objective function space. So whatever the result you get, you can basically just assume that that's a local solution. And basically, you just take that local solution and it's good enough. If you're finding that your fit isn't good, you can actually redo the fitting and come away with a different model. So the combination of random input parameters and a highly non-convex NLP problem means that you actually get a different result each time you fit. So you can run the same exact code with the same exact data and the same exact model structure, and you can actually get a totally different model each time you do that. So it might take several tries to get a neural network fit just right, and obviously this is implying that there is a lot of human intervention to make this work, and that's true, but there are certainly ways that you could automate this model selection. A really simple way would be try some initial weights, have some performance metric on how well it's fitting, and if it's not good enough, you redo it, try different initial weights, and just do this iteratively until your convergence criteria are satisfied. So that would be a simple way of automating that process, but there are certainly more sophisticated ways out there. One thing to keep in mind when you're looking at your residual, so I'm showing here some parity plots from the MATLAB neural network toolbox. So we're looking at this is the actual data, and this is our model data. So we want those to lie perfectly on this one-to-one line. And actually, they're not doing a terrible job. Here we have an R-squared value on our training data of 0.924, so that's in some cases might be considered to be a good R-squared value, but as an engineer and as a person who's used to working with data, you can see there's something weird going on here, and you're seeing that these residuals are correlated. So you see these weird offshoots here, and there's obviously some correlation where in a particular range of our target space, we're getting our model is predicting basically a constant value. So just in general, you don't want to have these correlated residuals. For example, if your model should be predicting something here, if this is your data, well, is your model going to predict this one, or is it going to predict this spot, or is it going to predict this spot? So this correlation is generally a bad thing, and you can generally, and it's not too hard to develop an eye for what's a good-looking fit. So the point here is that even though the R-squared might look good, that's definitely not the only metric you should look at. So you want the residuals to look like random noise. So you basically want to see an evenly dispersed cloud of data around that y equals x line to have a truly good model fit. So in instances where this happens, you might need to refit the model, or you can adjust the model and give this another try. So when I generated this data, I literally took this exact code, didn't change anything. It had the same input data, it had the same model structure, and it had the same fitting routine. I just went and hit play on my code again, and I got this data set. So I had just converged to a different local minimum from here to here. So basically the guess of random input parameters was just a better guess in this case. And as you can see, at least superficially, this looks fairly randomly scattered about that y equals x line. So again, as I mentioned, everything in this fitting routine was identical. So we just happened to have found a better local minimum in this case. So that's the end of an overview on how neural networks work. It is pretty high level, and you can certainly take entire courses just on machine learning and just on neural networks. But this is the basic idea, and it's actually quite easy. These toolboxes are very powerful and can do a lot of this. So we'll demonstrate how to use one of those toolboxes in MATLAB, so MATLAB's neural network toolbox, to develop and fit a neural network model to an actual data set. And that will be in our next video lecture.